Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we are going to solve BST validate. This prompt states you're given the root node of a binary tree, and you want to write a function that returns true or false if the binary tree is also a binary search tree. So if we look at this first example, it returns true because all the items left of every node are smaller and all the items right of every node are larger. In our second example, it returns false because this 10 is larger than 9, even though it's to the left of it in its subtree. This question has a few constraints. The first is that the tree won't be empty. We're guaranteed to have nodes. The second is that the tree will not contain any duplicate values, or the value stored in its data property will appear at most one time. And finally, we're going to use standard binary tree nodes. These nodes will contain a data property and a pointer to its left and right child. If it has no children, it will just point to null. So we are going to define a binary search tree as one where all the nodes to the left of any given node are smaller and all the nodes to the right are larger. So a left subtree looking at any node will all have smaller items, and then a right subtree must all be larger. So the example here is a valid binary search tree. However, now let's change one number. Previously we had 48 here, and now we're going to update that to 90. 90 now breaks this constraint. We have the number 50 here, but 90 is in 50's left subtree, and it's larger than 50. So it broke this constraint and is not a valid BST. So all the items in the left subtree must be smaller, and all the nodes in the right must be larger. So it satisfies part of the constraints. It's larger than 40 and 45, which is what we want. This means it's valid going to the right. However, it's also larger than 50, and this is what makes it invalid. Because this node is to the left of 50, it must be smaller than that value. So if we look at our root node, all the items to the left of it must be smaller than 50, and all the items to the right must be larger. So then what if we check this next node down, 40? All the items to the left must be smaller than 40, but then all the items to the right must be greater than 40 and less than 50, because 50 is now the upper bound to this left side. So now we have a range that the values can take when they go right of 40. Then, if we go down to 45, all the items to the left of it must be less than 45, but they still must be greater than 40 because it's part of 40's subtree. Then when we go to the right, it must be greater than 45 and still less than 50 because 50 is the maximum for this left side subtree. So we can see what we're doing is every time we make a move, we're setting bounds that any given item can take. When we went left, we now had this upper bound of 50. When we went right, we now had this lower bound of 40. But then when we went left again, we saw that 45 was now our new upper bound for 42. So because 45 is smaller and lower in the subtree, it becomes the new upper bound to the items going to the left. So we can see that when we move left or right, we can't just consider the current node's value. When we go right of 40, we can't say it only can be larger than 40. We also must consider that there are other nodes that constrain what it must be smaller than as well. So we're setting bounds whenever we take a right or a left move. If we went left from 40, now 40 becomes the current upper bound instead of 50, because 40 is smaller than the previous upper bound and lower in the subtree. So the realization that we made is that we must check bounds at every move and update those every time we go left or right. Specifically, when you go right, you have a new lower bound, and when you go left, you have a new upper bound, because that node becomes either the new maximum or minimum for any given subtree. So let's walk through our full invalid case now and see what the bound is every time we make a move. We're going to initialize the lower bound to the smallest number in our language, we'll call it negative infinity, and the upper bound to the largest number, we'll call it infinity. We use the most extreme bounds just to ensure our initial range is entirely open. When you start, all items will be larger than the lower bound and smaller than the upper bound. So we can see here, 50 is clearly within this range, so we're initially valid. Then when we move either left or right, we're also guaranteed to have the lower and upper bound adjusted accordingly. So let's start. First we go left. Since we went left, we're going to have a new upper bound, which is 50, so all items must be smaller than 50. 40 is, so we're still valid. We go left again. Our upper bound is adjusted to 40, 30 is less than 40, so we're still valid. We go left again, 30 is the new upper bound, 20 is smaller, so we're still valid. So we return true, and now we're ready to go right. Well, 50 was our previous upper bound, and now when we go right, we also set our lower bound to 40. So all items must be larger than 40, but still less than 50, because they exist in 50's left subtree. 45 is valid, it's between this range. So we go left. Now our upper bound is 45. So anytime we go left, we always change the upper bound because all items must be smaller than this item. Our lower bound is still 40 because we haven't gone right since moving into 40's right subtree. And 42 is between this bound, so this is valid. Now we go right. We update our lower bound to 45 because all items must be larger than the previous node when you go to a right subtree. And our upper bound is 50. So if we retrace our steps, we only made one left since 50, so it's the upper bound, but 90 is not within this range. So now we know we don't have a valid binary search tree. We return false. We want this false to propagate upwards. And now that we finished the left side, our right side will already be in the stack, so we traverse right as well. We continue to update the lower bound each time we go right, so 50, 55, 60, and our upper bound stays at infinity. All these items are increasing the whole time, so they're between the bounds. Then we reach the leaf node and return true. This propagates upward, but now we're back to our root node. The left is false and the right is true. So we want to make sure this false propagates upward, so if we find any falses, it needs to take precedence over a true. So we return false to our initial function call and get false as the solution. The key to this problem is managing that lower and upper bound. Specifically, anytime we go left, we decrease the upper bound because all items must be smaller than this new bound and they're always decreasing left. Or if we go right, we increase the lower bound because all items must be larger than this node and it's always increasing to the right. We're going to perform a depth-first search traversal, and specifically it's going to be a post-order traversal that will implement recursively. We're using post-order because we want to go down to the leaves, and if we reach the leaves, that means all the items are true. However, we have another base case where we check if a node is invalid, and if it is invalid, then we immediately return false and propagate this false upward. The big O complexity of our solution is linear time and linear space. We have to traverse all n nodes to determine if it's valid or invalid for a binary search tree, and in the worst case, we're going to have to add all n to our call stack. I also quickly want to walk through another alternate solution. We know with an n-order traversal, it will print all the nodes in increasing order. So it visits the left node, then the middle node, then the right node. If we do this for all items and all subtrees, that means the left is going to be the smallest, the middle is going to be between those two, and the right is the largest. So if you perform an in-order traversal, you can also just check that each item is always increasing to validate your binary search tree. So let's perform our in-order traversal now. We start by pushing forward to our stack, and then we go left before visiting the current node. So we have 2. Then we go left again before visiting the current node. So we have 1. 1 is a leaf node. So we check its value. Obviously it's the smallest because it's the first item. Then we check the current node. 2 is larger than 1, so we're still valid. Then we go right. We have 3, which is larger than 2. And now we've checked all of the left subtree from the root node. So now we visit the root node itself. It's 4, and now we continue right. we add 5, there's no left items, we check the current item, it's larger than 4, and then we go right again. There are no items to the left, we push 6, we visit that node, and it's larger than the previous item. So we can see that by using in-order traversal, it's always going to go left, then check the middle node, then go right. This is exactly how a binary search tree should be ordered if it's valid. So you always just check that the current item is larger than the previous, and if this is true for all items, you have a valid BST. And now we're ready to write our solution function isBST. We're actually going to recursively solve this function. So we'll start with isBST, but then call our recursive helper. So let's start there. So this function takes in the root node, or the current node, and then we pass it the lower bound and upper bound, which we're going to update as we make our moves left and right. We'll start with our base cases, and the first is just when you hit a leaf node, or the current node is null. Finding a leaf node means all the items along that path were valid. They were all either larger than the upper bound or smaller than the lower bound, so we never returned early, indicating we had a false value. Therefore, true is returned upward for all those items, and then we compare it to the result of other paths. The other base case is when we find an invalid node. So its data is less than or equal to the lower bound or greater than or equal to the upper bound. So it's not within the allowed range that can be valid. If this is the case, then we simply return false. And now finally, we want to do our recursive traversal, where we increase the lower bound when we go right and decrease the upper bound when we go left. So when we go left, we have the same lower bound. Moving left indicates the child node must be smaller, so there's no change to the actual lower bound at this point. But we do have a new upper bound. Because we go left, that means all the items to the left must be smaller, so the current node's data is now the maximum value for all the child in its left subtree. When we go right, we update the lower bound. This is because all the items must be larger than the current node's data. But there is no change to the upper bound. And finally, we return the results of our recursive functions. If these are both true, then this returns true. If either the left or the right is false, false will be returned. So what we're doing is using the and short circuit operator, which means if the left side is false, then it just returns false, or if the left side is true, it moves to the right side, and then it will return whatever the right side is. So this guarantees if they're both true, we get true, or if either one is false, we will return false from the function. And finally, we just need to call this recursive helper from our main function. So we pass the root node to our recursive helper, and we initialize the bounds to -infinity for the lower bound and infinity for the upper bound. We run our code, and our tests pass. So what we're doing is recursively traversing our tree. If we ever reach a leaf node, that means all the items to get there are true. If we ever find that one of the items is smaller than the lower bound or greater than the upper bound, it must be false. So then this base case returns false. We recursively traverse each node, and we update the upper bound when we go left, and we update the lower bound when we go right. These will all return booleans, And then we just return the result from the left and right traversal. And since we use an and short circuit operator, if they're both true, it returns true, or if either is false, it's going to propagate this false value upwards. And then finally, we return the result from our helper function from our main function. And that is our solution. Thanks everyone, and I'll see you in the next lesson.